Hello students, welcome to the third session of our first module and the subject mechanics of solids. Students, in the previous two sessions we have discussed the basics of mechanics of solids, how it is different from engineering mechanics or rigid body mechanics, and we have learned the very important two concepts called stress and strain, right? So hope you all are clear with those concepts. Okay, today we can discuss about the relationship between stress and strain. So students, how stress is related to strain? How stress is related to strain? So that is what we are going to learn. So the relationship between stress and strain is nothing but we call Hooke's law. Hooke's law. So students, before moving to Hooke's law, let us understand what it is meant by elasticity. What is elasticity? Students, if we have a rod with some any type of cross section, I am applying a tensile force of F. Okay, tensile force of F. So what will happen? When force is acting on tensile force is acting on F, it will get elongated. So initially it was of a length L. So initially it was of length L, and after the application of a force L plus delta along the size of that rod becomes L plus delta L. So there is an change in dimension, that is a kind of deformation is taking place. So we have strain epsilon equal to delta L by L. So this is strain. So application of force produce a strain. Okay, application of force produce a strain. So epsilon is nothing but normal strain. Normal strain in case of normal force. Tensile and compressive force are normal force. So epsilon. So what happened when there is a strain? So this was a force. So this was the elongation, force F. So as the rod get elongated, what will happen? What will happen? An internal force get generated, which opposes the action of external force, which tries to uh, pull back the material, right? The elongation, to counter the effect of elongation. So this internal force divided by area, the force internal force divided by area gives the stress. Internal. So once force is applied, strain develops. Once strain develops, internal force is generated. Internal force try to counter the effect of applied force, and thus stress is formed. This internal force or resisting force divided by area gives stress. So if we cancels this force, or if the force is removed, if the force applied force is removed, what will happen? The rod gets the size of the rod will be, what will happen? It will regain the size, right? once the force is once the force is removed, so this was elongation. Once the force is removed uh, from this length, it will regain its original length, right? Regain its original length. So that is what elasticity means. If an object is able to regain its original size or shape, if an object is able to regain its original size or shape, if the applied force is removed, if the applied force is removed, then the object is said to be elastic. Then the object is the material is considered as elastic, and that property of regaining size or shape is known as elasticity. Elasticity is the property of that material to regain its size or shape if the applied force is removed. So sometimes I have a body or a rod. So it was elongated by the application of a tensile force F. So even if I remove the applied force, it may not regain its size or shape. It remains in that elongated position itself. It remains in that if the material or object remains in that deformed position, even if applied force is removed, then material has reached plastic stage. Reached plastic state. Plastic state. So that property is known as plasticity. Plasticity means even if the applied force is removed, it won't. The deformed position will be remaining as it is. So it won't regain its original size or shape. Okay, it won't regain its original size or shape. So that is why we call the word plastic. We call some materials, some special types of polymers as plastics, right? Why that name plastics? Because even if we apply the force and if we remove the applied force, it won't regain its original size or shape. Most probably, those plastics will get what ruptured or crack, right? So that is why the name plastics. Elastic objects are those objects which regain its size or shape when the applied force are removed. So normally, an object when applied with force, uh, it will start to elongate. But after, if we increase the force, it will again elongation, continuous strain, continuous, those objects will continue to get strained. So you continue increasing force, continuous increase in force, reach a particular level. So initially if the force were removed, it may regain its original size or shape. That for a particular limit, up to a particular limit or a particular value of force, the the material will be elastic. The material will be elastic. After after a particular value of load applied load, the material will no longer will be elastic. So after a particular value of force, even if you remove the applied force, the material won't regain its original size or shape. It will remain as it is. So there is a limit for the value of force that can be applied so that the material remains as elastic. After that particular value, the material will become plastic. So the plasticity property comes into action. So that is the idea of elasticity and plasticity. So we started from here, stress strain relation. So this relation is nothing but Hooke's law. Actually, what is Hooke's law? Actually, Hooke's law is nothing but Hooke's law. Stress is always proportional to strain. Stress is always proportional to strain in the elastic range. Within the elastic limit. Within the elastic limit. So if we are applying a force, any axial force or shear force, whatever the force be, the application of force will generate strain. The strain will develop stress in that body. So the developed stress will always proportional to strain as long as the material is in its elastic limit. That is very important. Very important. Elastic limit. As long as the material, the loading is within elastic limit, the stress developed will be proportional to strain in that body. So if the applied force crosses the elastic limit, then the stress will no longer proportional to strain. So the stress proportional to strain will be applicable only if the loading is within elastic limit. Okay, so that is Hooke's law. Stress proportional to strain means stress is equal to a constant into strain. To remove proportionality limit, I have multiplied with a constant. Okay, stress by strain equal to a constant. So this is the mathematical expression for Hooke's law. Okay. So in case of normal stress sigma, either tensile or compressive, sigma equal to sigma by normal strain is epsilon equal to what? E. So the constant is called as E. This E is nothing but modulus of this E, constant E is called as modulus of elasticity. Modulus of elasticity is nothing but modulus of elasticity, or another name is Young's modulus. Okay, students, Very important. E is nothing but modulus of elasticity or Young's modulus. So sigma is nothing but E into epsilon. E into epsilon. So what is the unit of E? Unit of E actually E is equal to sigma by epsilon, right? Sigma's unit is Newton per meter square, right? Force per area or Pascal. By epsilon's unit is nothing but, so there is no unit for epsilon, right? Because epsilon is delta L by L. L and L is having same unit, so no unit for epsilon. So the unit of Young's modulus is nothing but Newton per meter square or Pascal itself. So in case of shear stress, right? Shear stress is proportional to what? Shear strain. So how we use shear strain as gamma. Sorry. So shear strain is gamma. Okay. So tau by gamma is equal to constant called G. So this constant is nothing but modulus of rigidity. Okay. So this constant G is nothing but modulus of rigidity. So this is the equation in case of shear stress. The other modulus of elasticity was the equation was the constant in the case of normal stress. So here shear stress, there normal stress. Okay. So this is what Hooke's law is meant by. So important within elastic limits, Hooke's law is valid. Hooke's law is valid. Okay, very important. So unit of G, modulus of rigidity, will also be what? Pascal or Newton per meter square. Okay, Newton per meter square. Now we have to move to uniaxial tension test. Uniaxial tension test. So this tension test is used to study about the material behavior or the mechanical properties of that particular material. So uniaxial tension test. So when you are going to do your lab work in strength of materials lab, so you will see a big machine called universal testing machine or UTM. So there you are using tensile force to calculate the stress and strain formed while applying force on that particular rod with any type of cross section, whether rectangular, square or circular. So we can study the relationship between stress and strain using that uniaxial tension universal testing machine. So in uniaxial tension test, we can get stress strain behavior or relationship even within elastic limit and outside the elastic limit also. Okay. So even within our outside both the range. Anywhere we can determine the stress strain relationship if we do some uniaxial tension test. So what is happening in this test? So this is a static type test. Static type test means we are not continuously increasing the force, but once we increase the force, we will wait. We will stop that that change in force until we record the strain or strain formed in that uh, the specimen. Okay, so that is why static type force is not continuously increased. Continuously change. Force is not changed while we take observations. Okay, so that is why it's static type. We use a word called static. So there will be standard specimens used for tension tests. Okay. This is a type of, I will show you. So this is the two standard type of specimens used in universal tension test. First one is with circular cross section. Second one is with rectangular cross section. Okay. So please note it down. These are two types of specimens. So students, I have drawn that kind of specimen here. So students, so these two, these two part of that specimen is for what? Is for fixing fixing that this specimen in that particular machine. Okay, right? So actually this length LG is where we fix gauge or the gauge length, the length of specimen on which we want to determine the mechanical properties. So in this particular length, we are interested to find the mechanical properties in this length only. Gauge length, LG means gauge length. Okay. So even though the total length is L, the whole part is not used for studying the mechanical properties. These parts are used to fix this particular specimen in that machine. Okay. Here only we are studying the mechanical properties or the change in length or stress or strain. Everything is studied here only. So here we will fix a particular, here in this section we will use a particular instrument called gauge. Okay, we will fix a gauge here to understand the change in dimensions. So you can see all these things in your labs when I think you will have to do strength of materials lab in this particular semester itself. So you'll get more idea when you see those things. Okay. Now what is actually doing in this particular test, universal uniaxial tension test? What is actually we doing here? So the ends, So LG is nothing but gauge length. Okay. Okay. What are the steps in uniaxial tension test? First one, we are going the ends of the specimen are secured in the grips of testing machine TM, testing machine or universal testing machine TM. Okay, so this is the first step. Second one, there is a particular unit, unit, what for applying load, force, for applying load or force, load to the specimen, either by hydraulic or mechanical. So there is a load, there is a unit, a particular unit for applying the load to that specimen. It may be either hydraulic or mechanical, right? The third step is nothing but there will be some recording device, recording device by which we measure the final output in the form of load or stress, Okay. So the testing machines are often equipped with some pendulum type lever or pressure gauge or hydraulic capsule, which will help us to record the measure the load or stress. Actually, we are measuring the load. If we measure the load, we will get stress, because stress is nothing but load by area, and there will be some gauges to measure the deformation or elongation happening in that particular section of that specimen. Okay, so actually what we are doing, so we are fixing using this end, and we will fix some gauge to measure the change in length. Okay, change in length. Actually we are applying tensile load on that uh, on that particular specimen. So what will happen, we will apply force, we will increase the force and measure the force, and accordingly we will measure strain or deformation, and we will plot this. If we have for each particular force we will have deformation, so we can have a graph between force versus deformation. If we divide force by area, we will get stress. If we divide deformation or delta L by actual length of that section, you will get, here we will get sigma, here we will get epsilon strain. So if we are drawing a force versus deformation graph, means we can draw a force versus stress versus strain graph also, right? So we will get stress versus strain graph using uniaxial tension test. Uniaxial tension test. Okay. So we can plot a graph between sigma in y-axis, strain in x-axis. Why we are taking strain in x-axis? So this is y, this is x. So y epsilon in x-axis, y. Can you guess? Actually, in x-axis, if we are plotting two parameters in a graph, in x-axis, every time we plot the cos, the parameter actually the parameter which causes the effect. The effect will be in y-axis only. Cos will always be plotted in x-axis. Effect will be plotted in y-axis. Students, you must always keep in mind that in x-axis always we plot cos. In y-axis the effect. This is applicable in any subject and any problem. Okay, I'm not specifying this for this particular problem only. So this is applicable in anywhere. Okay. So here in our case, the cause is nothing but strain. Actually, strain causes stress, right? When force is applied, the elongation takes place. So elongation takes place means strain happens. When strain happens, in order to counter effect the strain, in order to bring back the body to its original size or shape, internal force gets generated. This internal force divided by area is stress. So strain causes stress. Okay. So strain must be plotted in x-axis. So the stress must plotted in y-axis. So here sigma in y-axis, strain in x-axis. So I will draw a typical tensile test curve for mild steel. So this curve may vary for different materials. Sorry, material mild steel, for mild steel. Mild steel. Okay. So listen. Initially at 0, when strain increases, stress also increases. Okay, I will explain all the points. Don't worry. Let me draw it first. A, B, C, D, E, F. So students have this graph for stress versus strain graph that we have obtained for mild steel when it is undergone an uniaxial tensile test. So students, initially you can see sigma increases linearly with epsilon. That is, stress increases linearly with epsilon. So this range is linear. I will use another ink. Linear, right? So linear means sigma is directly proportional to strain. So up to the point A, uh, the sigma is proportional to up to A. So that means Hooke's law is valid. So A is called limit of proportionality. The point A is called limit of proportionality. Note it down. A is nothing but limit of proportionality. So it is evident from the graph that strain is proportional to strain, or elongation is proportional to the load, giving a straight line relationship or a linear relationship. So this law of proportionality is valid up to a point A. So we can say that point A is some ultimate point when the linear nature of the graph stops. After A, the graph is not that much linear, some curvy. Here it must become curvy. After A must be the graph should become a little bit curvy. It may not be evident in this particular drawing that I have drawn. Actually, after A it should be curvy. So the not strictly linear. Okay. So the point A is called the limit of proportionality. So here Hooke's law is valid. Hooke's law. Hooke's law valid since it is proportional. Okay. Now after A, what's happening? So after A, we can see a point called B. So for a short period beyond the point A, the material will be still elastic in the sense that deformations are elastic means deformations will be completely recovered, or the original size will be re-established or recovered when the load is removed. So the B is known as elastic limit. B, elastic limit. So students, you must carefully study this graph. So this graph is very important, stress strain graph. Okay. So the point A is proportionality limit, B is elastic limit. Means up to point B, the material will be elastic. That is, when if the load is removed, it will the original size or shape will be recovered. Okay. Okay. So B is elastic limit. Then what happens after B? After B, beyond this elastic limit, B means elastic limit. So it means that after B, the material will become plastic, right? So it has already reached elastic limit. Even if we increase the load F, then and after increasing the load, it reaches plastic range. After reaching plastic range, even if you release or remove the applied load, it won't regain its original size or shape. So this is uh, after B plastic range. Plastic range. It has reached some plastic range. So the material is no longer elastic. Okay. So beyond this elastic limit, plastic deformation occurs and strains are not totally recoverable. That's the important point. So there will be this permanent deformation when load is removed. So even if load is removed, the deformation remains permanent. It won't be recovered. So the points C and D are termed as upper and lower yield points respectively. Okay. C and C upper yield point. Upper yield point. D lower yield point. Yield point. Okay. Uh, so, so the stress at the yield point is called yield strength. So this particular at C, the stress is called yield strength. The value of strength is the value of stress sigma y. The value of stress at C is called yield strength. So C and D are yield strengths. What is meant by yield points? Upper yield point and lower yield point. So this means that the materials start to yield to the applied force. Yield means it start to deform plastically. Deform plastically. So that is the meaning of yield point. Okay. So there are two types, two yield points. Actually here, even if the strain is increasing after upper yield point, the stress starts to decrease to C to D. Epsilon increase but sigma decrease for a short range C to D up to lower yield point. Even if the strain increase, sigma starts to decrease. That is due to a particular plastic set formation within the material. So you can learn the reason for that decrease in your higher classes, or I will explain those that particular property in separate class. Okay, don't worry about that. You just keep it in mind that for a short range C to D, when strain increases, even though strain increases, sigma decreases. Actually, whenever strain increases, stress should increase, but for this particular span C to D, even if strain increases, stress seems to be decreasing. This is actually happening due to a particular rearrangement of molecules or molecules within the material in that plastic range. So since the plastic range starts at C, actually there is happening some rearrangement of molecules, and up to D the sigma decreases, but after D again sigma increases with the sigma increases with the epsilon, that is stress increases with the strain. Okay, so from lower yielding point, what happens, it continues, the stress continues to increase, a further increase in then, and after increasing the load further from D, load is increased from D, sigma increase, the strain increases as well as stress also increase. A further increase in the load will cause marked deformation in the whole volume of the material. So the maximum load here at point E, the maximum load which the specimen can withstand without failure. So this is the maximum load, sigma maximum or ultimate sigma u. So this is the stress at maximum load is nothing but ultimate strength sigma u at E, ultimate strength. Ultimate strength. So at point E is the point at which maximum load is possible. The maximum load that the specimen can withstand without failure. Without failure means any cracks or any cracks or breaking of that particular specimen is happening. So that is the idea behind. That is the idea called failure. So the maximum load with which the specimen can withstand without failure is called the load at the ultimate strength point. The highest point E of the diagram corresponds to the ultimate strength of that material. So sigma u is the stress which the specimen can withstand without failure. Okay, ultimate tensile strength. So after E, what is happening? After E, what happens? Beyond point E, the bar begins to form next. What is neck formation? Neck formation takes place after E. Neck formation means if this was our specimen, after E, it will form some necks, that is a decrease in the cross section. Along with the increase in length, along with the increase, the length will get increased. That is what deformation or elongation takes place. But at some area, the cross section of that particular specimen get decreased. So that process is called necking. It decrease means it is almost about to fail. Some cracks or failure is about to happen. So that is what neck formation means. To the load falling from the maximum until fracture. So at point F, fracture occurs. Okay, at load F, fracture occurs. So beyond point E, the cross-sectional area of the specimen begins to reduce rapidly. After E, up to E, there is only elongation taking place. The length of the specimen get increased, but after E, the length of the specimen also get increased, but the cross section of the cross section of that the particular specimen get begins to reduce or get decreased rapidly over a relatively small length of that bar. So that is called necking. So necking takes place while the load reduce, whilst the load reduce and the fracture of the bar finally occurs at point F. So students, there are two types and I have shown two types of graph here. First one is nominal and second one is true. So what is the difference between nominal and true? True stress strain graph? Nominal and true stress strain diagram. This is true stress strain diagram. This is nominal. Okay, I will show the difference. Actually, nominal stress strain graph, here stress are usually computed. Calculated stress calculated on the basis of original area of the specimen. Such stresses are called normal stress because original area cross sectional area, okay, original cross section area of the specimen. But students, you just came to know that after the point E, the necking start to takes place, right? The cross sectional area start to get reduced rapidly after the point E, after that particular point E, or maybe after D itself. After D, the point D itself, I will show. Okay, after point D itself, the cross section of that specimen start to decrease slowly, but after point E, the decrease in cross section will start more rapidly reducing. Okay, so in case of true stress true stress true stress strain graph, actually stress is calculated uh, by on the basis of actual area, on the basis of actual area actual area. So because actual area is getting reduced after D, after E it reduces even more rapidly. So the graph drawn with the stress calculator on the basis of actual area is called true stress strain diagram. So actual area is actually getting reduced. So the true stress strain graph will in the true stress strain graph, the stress will always increase. You can see here. So this is nominal. Here true. True means true will always increase because this here sigma is calculated. Sigma is calculated based on actual cross section at each instant. At each instant, the actual cross section is getting reduced, so that sigma always increase. But here it is based on original the cross section area that was used in the beginning of tension test. So that same area is used in nominal uh, strain graph. So that is why this gets dipping. This is in a dipping manner. So up to f, here it will increase. So normally we use nominal graph itself. Okay, nominal graph. If you are asked to draw the stress strain graph in your exam, you just draw nominal graph, nominal stress strain graph. So the point F is also known as a rupture strength. Okay, a rupture strength. Since after necking, the necking goes on or continues up to the rupture of that or failure of that object happens. So f the sigma the point the stress corresponding to the point f is known as a rupture strength. So hope you have understood this stress strain relationship between the stress strain relationship for a mild steel, uh, and you have understood the Hooke's law. Okay, so as of now I will stop this session. Thank you.